So today we're going to be looking at 9.4, which is the distribution of the sample proportions. And this is very similar to 9.3. The only difference is that now we're going to be looking at proportions instead of means. So what we've said before is we normally have a population and we're going to take a sample from the population and then we're going to find the mean of that sample. So it can tell us something, as long as it's a representative sample, it will tell us something about the mean for the whole population. We're going to do the same thing now, but with proportions. So we're going to take a whole population. Let's say you've got a production line for a manufacturer. You take the whole population. You want to see, okay, I want a rough proportion of like how much of this production line is faulty. So they want to see how many of their components are defective, let's say. But trying to do that for an entire population on a production line is incredibly difficult. So what we do instead, and we did this with the Lay's potato chips example in class on that video, you take a sample instead and you see what proportion of the sample is defective, and that should give you an estimate for how much of the population would be defective. So two things that we need to first start out with is some notation. So I'm going to say that P is going to be the population proportion. So that's the thing that is very, very hard to find. So P is the population proportion, and then the sample proportion for any sample that I take, I'm going to call that P hat. Okay, so I'm going to, as long as it's a representative sample, I'm going to use my sample proportion P hat to estimate my population proportion P, because it's very, very difficult to find the proportion of a whole population that had a particular characteristic. For example, what proportion of things are defective on a production line. So the way that you find a sample proportion, and we've done this before, it was one of the chapters on the homework, is by doing X over N. X is the number of things in the sample that are defective or have a certain characteristic. Okay, and N is just the number of things in the sample. Okay, so that would give me a sample proportion, okay, the proportion of people or things that have a particular characteristic out of the N things or people that I start with in my sample. So as I said, as long as you take a representative sample, you should be able to use P hat to estimate P. Okay, that's the whole point of taking a representative sample. What we're now going to do is look at the distribution of those sample proportions. So we did this when we did sample means. We looked at the mean of the sample means and we looked at the standard deviation of the sample means, and we saw that this thing actually took on a normal curve, so that normal distribution bell-shaped curve. We're going to do the same thing here. We know that when we take proportions, okay, and when we take samples, what you should find is that half of those sample proportions for whatever size sample you take, half of them should be less than the population proportion and half of them would be greater. This is what you'd expect whenever you took a sample and then you took the proportion for the sample. You should find that half of them lie below the population proportion and half of them lie above. So what you actually find is that the mean of the sample proportions, when you take multiple samples, the mean of the sample proportions should be the population proportion. Okay, if you look back at the number line from 9.3, it's very much the same. Our population proportion should lie in the middle and our sample proportion should lie either side of it. But we want those sample proportions to lie as close to that population proportion as possible. Okay, so we don't want these sample proportions to vary very much from one another or from the population proportion. We want them all very close together, which means that we want that variance to be as small as possible. What we do, again, we can take a standard deviation. Okay, the variance of the sample proportions is just the square of this value. So the standard deviation of the sample proportions, don't worry about where this comes from. You won't need to know that, you just need to know what it is. It's the population proportion multiplied by 1 minus the population proportion divided by n and then square root it. Okay, by square rooting it, we go from the variance to the standard deviation. So the variance would just be the square of this value. But as I said, normally you don't have that population proportion. Okay, you normally have no idea what it is. So what we tend to do is we say, okay, I'm going to estimate my population proportion by using one of my sample proportions. Okay, and that should give you a pretty accurate indication of what the standard deviation of the sample proportions are, just by using that sample proportion instead of the population proportion, because you would hope that they would be very close together. Occasionally when you get a problem, they will give you the population proportion, but in real world problems, you normally don't have it. That's the purpose of taking a sample proportion, is so that you can kind of have a guess at what that population proportion is. So normally you don't have it. So just be aware that sometimes in problems you will have to use this second equation instead, just because you don't have that population proportion. So as I said, when you do this, you want that variance to be fairly small, which means that you would like your sample size to be fairly large. Okay? If you think about it, the larger the sample size you take, the closer that sample size is going to get to the size of the population. Okay? So let's say you had 200 things in your population. You took a sample of 10 of them. Well, each time I take a sample of 10, I'm not really getting as accurate a picture as I might if I were to take 100 things in my sample. Okay? 100 things is way closer to 200, so you would assume that you would get a more accurate picture by using more things in your sample. So the more things you use in your sample, the closer you would expect these sample proportions to be to your population proportion. And that makes sense here, because the larger the n is, it means that the smaller this fraction is going to be. So the smaller that fraction is, it means that the smaller my standard deviation is, and hence the smaller my variance is. So that makes sense. It all ties together. So the larger the sample size you have, the smaller the variance. The less that these sample proportions will vary in comparison to your population proportion. They will all be clustered around that population proportion. As we said, you would like the sample size to be fairly large. What we actually say, remember for the sample means, we said that we would like a sample size of at least 30. So you'd like a sample size of greater than 30. In this case, what they actually do is that they say that they would like both NP and n times 1 minus p both to be greater than or equal to 10. Okay, so we want the number of things in the sample multiplied by the proportion to be at least 10. That is what we count as a sufficiently large sample in this case. So just be aware of that. It lines up with that binomial. When we did 8.6, when we did an approximation to the binomial distribution using our normal distribution, it actually comes alongside with that. It's actually exactly the same characteristic that you have to have to get a reasonable approximation here. So we would like n times p and n times 1 minus p both to be at least 10 to get this thing to have a normal distribution. Okay, it's exactly the same as what we did in binomial. If you think about it, you're looking at the proportion of things that have a certain characteristic. So there's going to be, the rest of them are not going to have the characteristic. You have two outcomes, it's actually binomial. So if you think about it that way, this thing will then actually take, in order for it to take on a normal distribution, exactly as we said in 8.6, to take on a normal distribution and to use that normal approximation, we had to have these two properties. So make sure when you do this, I'll write this over here. In order for the sample proportions to take on a normal distribution, we must have NP is greater than 10 and N times 1 minus P is greater than or equal to 10. And then you can say that the mean of the sample proportions is just the population proportion, and the standard deviation of the sample proportions will be one of these two. It's actually equal to this, but you can estimate it by using that sample proportion instead. Okay. So this is exactly the same theory as we did with sample means. We are just now applying it to proportions instead. So I'm going to go through an example. This is actually in the notes, and it says that a 5th grade teacher calculates that 27% of her students are late for class. If the teacher is correct, what is the probability that the proportion of late students in a sample of 724 would differ from the population proportion by less than 4%? Okay. So this is very similar to what we had before with the sample means. We are just now applying it to sample proportions, and we're going to do a Z transformation. So in our case now, remember before, when you are dealing with individual data points, where you've got a normal distribution, this Z transformation will take it from a normal distribution to a standard normal distribution. Transformation when we were looking at sample means, which was the sample mean minus the population mean divided by standard deviation over the square root of the sample size. Now we're going to do the same thing again. Okay, so now we're going to have our Z transformation is going to be our sample proportion minus the mean of the sample proportions divided by the standard deviation of the sample proportion. So now we are treating our sample proportions as our data points. So plugging in what we know, now again, if they do not give you that population proportion, you can use your sample proportion for this part. For the standard deviation of the sample proportions, you can substitute in that sample proportion that they give you instead of the population proportion. It depends on what data they give you. In this case, what she actually says is that a 5th grade teacher calculates that 27% of her students are late for class. So what we actually have here is they have said, okay, we know what our population proportion is. But 9 times out of 10, when they give you one of these problems, they will give you a sample proportion instead. So just be aware of that. So if you look at the notes again, it says that a 5th grade teacher calculates that 27% of her students are late for class. So we know that our population proportion is 0.27. If the teacher is correct, what is the probability that the proportion of late students in a sample of 724 would differ from the population proportion by less than 4%. So we want to know what the probability is that the sample proportion for this sample of 724 students, what is the probability that the sample proportion would differ from this population proportion by less than 0.04? So if I look at 0.04 either side of this, I'm looking at the probability that my sample proportion is between 0.23 and 0.31. Okay, now I need to do my Z transformation on this. So I'm looking at the probability of 0.23 minus 0.27 divided by, we're going to have the square root of 0.27, then 1 minus 0.27, which would give you 0.73, divided by n, which is 724, is less than or equal to p hat minus p over the square root of p times 1 minus p over n. And that is less than or equal to, and you're going to do the same thing to this side here, it's going to be 0.31 minus 0.27 over the square root of 0.27 times 0.73 over 724. Okay. When you plug this into a calculator, and you can plug in both sides here and here, you should get that this is the probability that you are between negative 2.42. This middle part here is just z, okay, from our above equation, which is less than or equal to 2.42. Okay, so we are looking at, we started with the probability that our sample proportion would be within 0.04 of our population proportion. What we have done is a z transformation, which takes that normal distribution of our sample proportions and now uses instead our standard normal distribution. So it has done a z transformation to take you from a normal distribution to a standard normal distribution. So when we do that, plug it into a calculator, you're going to have normal CDF of negative 2.42 as a lower bound, 2.42 as an upper bound, 0 for a mean and 1 for standard deviation, and you should get 0.9845. Okay. If instead it said, what is the probability that our sample proportion would differ from the population proportion by more than 4% or by more than 0.04, okay, what you have done here, let's draw a quick normal distribution, okay. What you have done here, if this is your population proportion, we've gone 4% either side. That's actually a really, really large gap there that I've drawn. But anyway, so we are looking at what is the probability that you fall within 4% of that population proportion. Okay, so we have found that middle area. If instead it said what is the probability that it differs from the population proportion by more than 4%, instead we would be looking at this area outside here. So what we would have to do in that case would be 1 minus what we found. Okay, and that would give you 0.0155. Okay, so if it said what is the probability that it differs from the population proportion by more than 4%, this would be your answer. But the question was, what is the probability that it differs from that population proportion by less than 4%? So this is your answer. Okay, so it's very much the same as what we did with our sample means. You just have to be aware of the fact that your sample, that standard deviation of the sample proportions is now different. Okay, so just remember what your z transformations are, okay, and what they are for your sample means and what they are for your sample proportions. Okay, so they both have a normal distribution, but trying to find what the mean of the sample means and the mean of the sample proportions is slightly different, and same with the standard deviation of the sample means and the standard deviation of the sample proportions is slightly different, but the actual formulation of it is exactly the same, and they both have a normal distribution. So we just do a z transformation that takes you from that normal distribution into standard normal distribution. You plug it into normal CDF with a mean of 0 and a standard deviation of 1.